Welcome to MC312 Thermal Fluid Systems 2. This is your lesson on Exergy in a closed system. This is the first of a couple lesson videos associated with this lesson. To be prepared for this lesson, you should have your textbook available. Open to section 12. Three lesson objectives today. The first is to define and explain the concept of Exergy, or the available energy in a system. And this is what is gone over in this video. The following video will help you with the second two lesson objectives, namely the calculation of Exergy for a state, as well as conducting a system Exergy balance for a closed system. Recall, a closed system is a system which only interacts with the surroundings without mass flow into or out of the system, so there's no inlets or exits. So you can still have work interactions and or heat transfer interactions with the surroundings, but there's no flow into or out of the system. Quick definitions. Energy, the property we've talked about most similar to Exergy, is the ability to do useful work. And Exergy is the maximum amount of the energy that is able to do work. So it turns out that not all the energy is able to do work, even though the definition of energy is the ability to do work. Another way to reference Exergy is to describe it as the quality of the energy, which is relative to the surroundings in which the energy is located. So look at the three cases on the screen there. You've got a 60-pound mass, 20-pound mass, 40-pound mass, all resting on the ground, in which case has the highest gravitational potential, or stated differently, the greatest potential energy. Well, they all have the same distance from the ground, and therefore the system with the greatest mass has the highest gravitational potential. But the problem is it doesn't seem like it has much because they're all resting on the ground. So let's spread them out a bit. Let's put case 2 with the largest distance from the ground. Case 3 is second largest, and so on. And so if the drawing is to scale here, you would presume that case 2 then has the largest gravitational potential energy because it's the furthest distance from the ground, and it looks like it's more than twice as far as case 3 is, which would be second. And there's no potential energy in case 1. This idea that it's relative to your surroundings, that's what Exergy is about. Here's a complex diagram that talks about the US energy consumption about a year ago. It uses units of quads, which are equal to 1 times 10 to the 15th BTUs, or for my SI system fans, we have something like 293 million kilowatt hours. So a lot of energy in a quad. You can see there on the left, the sources, the 100 quads that the U.S. consumes, 1 in solar, a quarter of 1 in geothermal, and the bulk in petroleum products. It's used for a variety of different features. Here it's broken up into residential, commercial, industrial, and transportation. I want you to focus, though, on the right-hand side. Delivered energy that meets the user's requirements is about a third. The other 2/3 is rejected. It's either used inefficiently, or it's unable to be completely transferred. You can see their electrical energy generation has a large taxus as the petroleum. Some of that's coming off in the petroleum as waste heat, unusable energy at some level. And so not all the energy, the 100 quads, can be used. In fact, only about a third of it can. This talks to the importance of Exergy. Where are those losses happening? Why do they occur? Okay, at this point, you should be open in your textbook to page 12-3, and we're going to talk about some definitions here. Thermomechanical Exergy, or EX, that's the property that we're going to call it, is the maximum potential useful work that could be produced by a system interacting with its surroundings. It's a system property, which means it can be extensive or intensive. So it can have a mass term in it, or it can be per unit mass. And so it's going to have units like energy or energy per unit mass. It must always be greater than 0. It is a subset of the overall energy of the system. And so as such, it's always greater than or equal to 0 if it's the dead state. And then finally, it's not conserved. I said previously, I'll reiterate that this is a description of the quality of the energy, the utility of the energy to conduct work. The dead state's another important concept related to the idea of Exergy, and it's either specified what the dead state is, or if it's not specified, then you're to use a standard atmospheric assumption, either 298 Kelvin, 101.3 kilopascals, or if you're in the English system, 537 Rankine, and 14.7 pounds per square inch absolute. So those are the temperatures and pressures that you use for the dead state, either the specified boundary conditions or the standard conditions in the absence of the specification. Perhaps a diagram will help us understand this concept of exergy more. If this is our system here in blue, and we surround our system with a local boundary, so these are our local surroundings here, which we're going to describe as having a dead state temperature. Notice the dead state has a subscript of O for dead state, or 0. You can have a pressure at that dead state, and other properties as you want, internal energy, enthalpy, specific volume, entropy, etc. And then the surroundings out here, generally we're going to say that they have a velocity and a gravitational potential datum that allows those values to be 0, where the system can be moving, it can have potential energy, but the surroundings we've identified in such a way as though they do not. So hopefully that's a useful construct to help you identify the system as it's related to its surroundings. Let's look at another way to visualize exergy. We'll do this here on a diagram here, a PV diagram. And so we'll make the y-axis the pressure axis, and the x-axis the volume axis. And we'll describe a system that has its initial state, I, somewhere here with the initial volume, P sub I, initial pressure, P sub I. And it has a second condition or related condition. This is the dead state condition here. That's dead state O, so that is then, and so this region under the curve here, that's energy related to the dead state. And then we can assume some process to get from I to O. We'll sketch it like that. And so this area hashed in blue there is the exergy of state I. Now the overall energy of state I is the dead state energy plus the exergy of state I. The exergy of state I is just the blue, whereas the entire area under the curve would be the energy of state I. Again, what's not usable? The hashed portion in red. When you can draw a PV diagram, you can almost always draw a TS diagram. Let's show the same thing. It's very similar on the TS diagram, and so we'll go through this quite quickly. And our initial temperature, Ti, our dead state temperature, To, entropy, Si, entropy, So, and again, let's just go ahead and do this. Our useful exergy, mind you, the must match between the PV diagram and the TS diagram. Both of them can give us a measure of the overall energy, and summarize here with the inexact differential work, as we saw from last semester. And because it's a closed system, it's only moving boundary work. And here we have the inexact differential of heat transfer being the integral of TdS. Okay, so these concepts are a reminder from last semester. This is the idea of exergy. Stay tuned to the following video as we talk about how to use exergy in a closed system.